Now that we have our pH titration, now what we can do is use that to answer some important questions. The first thing we want to do is find the equivalence point, and we'll find the equivalence point by looking at the vertical. This right here would be the center of the vertical part of the titration curve. This would be our end point. You would label it by writing down the x and y coordinates of that point. X, it would be about 50 milliliters. Y, it would be close to a pH of 9. Not quite right. Not quite there. Now, something important that's going to happen as we lead up to that is when we get halfway to the end point, halfway to 50 is 25, we have a point here. It's not the end point, but it's halfway to the equivalence point. And at this point in the titration, what's true is that the Ka is equal to the products of the equilibrium, which is H plus 1, A minus 1, over the reactants of HA. However, what we got to remember is that halfway to the equivalence point, these two are equal to one another, and so they eventually cancel out. What we're left with is saying is that Ka equals H, and if we take the negative log of both sides, we can say the pKa equals the pH. This is only true when we're halfway to the end point. So that's only true here. So I look at this and I say the pH is about 4.5. If the pH is around 4.5, that means the pKa is about, 4.5. And I'll take my handy dandy calculator. If I put in 4.5, make it negative, and then take inverse x of that, doesn't like that, 4.5, make it negative, take the inverse x of that, I can find my Ka to be around 3.2 times 10 to the power of minus 5. And then I would look at my list of possible Ka values and say, aha, it must be this acid or that acid based off of that. Okay? If I were trying to determine the molarity of the acid, well, I need a little bit more information. For instance, I need to know a couple things. And if I knew the sodium hydroxide was 0.420 molar, and the amount of the acid was 25 milliliters, then I could actually figure this out. What I'll do is I'll say that the molarity, or moles per liter, of the acid is equal to the moles per liter of the base, moles, not ml. The base is 1 liter, 0.420 molarity, times the number of liters of base. Well, how many liters would that be? At the end point, at this point right here, this is the equivalence point when the moles of hydrogen and hydroxide are the same. So what I can do is assume that that is where I have 50 milliliters, and that's the molarity. That tells me the volume and molarity of the base. Since the reaction is a 1-to-1 stoichiometry, the next thing I'll do is take this times 1 mole of acid over 1 mole of base. And then finally, to get our final conversion to this, then I can tell that I have a certain number of liters of acid, and from this information I can see I have 25 mils, or 0.025 liters. Putting all of that in my calculator, I come up with 0.84 moles per liter for the acid. What we can see here is that you have a variety of acids being shown, strong acid on the bottom, and then a weak acid with a pretty high Ka, and a weaker acid with a lower Ka, etc. What we're certain of here is that a titration curve shows the pH of a weak acid halfway to the end point. So if the end point of all of these is at 50, that means my halfway to the end point is at 25. And look what we see. Halfway to the end point, the pH is 2, the pKa is 2, the Ka is 10 to the minus 2. Halfway to the end point, the pH is 4, the pKa is 4, the Ka is 10 to the minus 4. Notice being a weak acid means the pH, as you approach the end point, is bigger value, but the pH at the end point is exactly the same. The end point of each of these is still at 50 milliliters because when you have any two acids, strong or weak, with the same molarity, their endpoint pHs differ, but the volume, the moles of hydrogen or hydroxide is the same. Notice here what we've got is a weak acid that's diprotic, and part of this is off screen. What we can tell is if we start off with a diprotic weak acid, you're going to have your first endpoint right about here, halfway up the vertical, and that's where we would have the first salt where you've lost exactly one hydrogen. The second endpoint is going to be right over here where we've lost our second hydrogen, and if you need a better picture you can look on your notes. And at this point we can imagine that halfway in between, the second endpoint is exactly and always double the first endpoint. So, for instance, if this is 50, this could not be anything but 100 because you're going to have the same mole-to-mole ratio. Halfway to the endpoint here would be at 25 mils, and here's another case where the pH, about 2, would be equal to the pKa of about 2. So a Ka of about 10 to the minus 2. Halfway to the second endpoint would be here at about 75, and halfway to the second endpoint is where we have the pKa of about, what is that, about 6.5, equal to the Ka of, I don't know, whatever that works out to be. So this is how I can use titration curves to answer the same kind of questions you'll find in your lab. So on your lab, remember, you have to identify the acids and you have to determine the molarity of the acids. That's what you need to do, and justify your reasons in a way that makes sense. All right, good luck.